Okay, in this video I'm going to be going through the ISP on further mechanics and EM fields. So it starts on further mechanics and goes into EM fields. And we're going to start with ISP task 1, which is talking about momentum in 1 and 2 dimensions, and also the idea of energy and collisions, that's elastic and inelastic collisions. So let's jump straight into the explaining everything task and see what we've got on there. Okay, so the first example is two balls colliding. Explain the velocity of the of a ball after a collision can be calculated by knowing the mass and velocity of balls before collision. Okay, so if we've got a collision taking place, right, thank you. Okay, if we've got a collision taking place between two balls, and if we know the mass and velocity beforehand, okay, we can figure out what it's going to be like afterwards. Remember, the mass will be the same as before, so let's call that mass before, and velocity before, and velocity before. Let's call those 1 and call those 2. Okay, so mass of ball 1 will be the same, as it was beforehand, and same with ball 2. Backlight on there just to make that a bit more visible. There we go. Okay, but the velocities will be different. Now the idea you need to tie in is the idea of the conservation of momentum. And remember, the conservation of momentum tells us, I'll write on conservation of momentum tells us that the momentum beforehand is equal to the total momentum afterwards. So remember, these are in opposite directions, so one of these will have a minus momentum compared to the other one. So this will be a positive momentum, that will be negative momentum, and this will be a positive momentum, and this will be a negative momentum, okay, because you can see they're going off in different directions. Okay, so maybe you need to take those into account. This works in 2 dimensions, okay, so if you've got something going off an angle like this, and another ball coming in like this, then afterwards momentum is conserved in both the vertical and horizontal dimension. At university you learn about the same in 3 dimensions. Okay, so that's how we do that. Next, describe an experiment that can be used to investigate the conservation of momentum. So we'll talk about light gates, air tracks and trolleys. Okay, so it's the idea of an air track having a light gate, having a trolley on top of it, with light gates connected across it. Okay, so if they were then connected to, say, so I'll just bring that all up so you can see it. So you've got two light gates, you've got one trolley there, another trolley over here. Let's add to this, and what we've got is an interrupt card on top of it, which interrupts the light gate. Okay, so the light gates will measure the time it takes for the card to go through. We need to input the distance, and therefore it can figure this essentially the width of the card, and therefore it'll figure out the velocity of each of these trolleys. By figuring out the velocity that they have as they come into the collision, by allowing the collision to take place in the middle, and then seeing the velocity they have afterwards, they can figure out, they can investigate what the momentum was like before and after the collision. So use the velocity from the light gate and the mass of this to figure out the momentum of this one, and do the same for this one, and then it comes back out of here. They again figure out the momentum afterwards and compare the two. We use an air track to minimise frictional forces, and remember, one of these can have a ratio of a certain mass to the other. You don't need to know the masses of these. It could be that one has mass x and one has mass 2x, so one could just be twice as massive as the other one. Excellent, excellent. So that's the explaining everything done. Now let's move on to some questions. Okay. Right, so we've got a football that's been kicked against a post during a football game. We've got the mass of the football on there, and it rebounds directly back into play. So it doesn't go off at an angle, it rebounds back into play. The diagram shows the ball colliding with the post. The impact speed is 27 meters per second. Okay, calculate the momentum at impact. Okay, so momentum, remember, is just mass times velocity. So all we're doing there is 0.42 times by 27. As straightforward as that. Not really much to the first question. So it's a pretty straightforward start for us. Okay, so that's somewhere in the region of 11. So 20, let's put my calculator shot, 27 times 0.42 Yep, it's 11.34 kilogram meters per second is the unit of momentum, remember. Okay. The ball speed at the moment it loses contact with the post is 10 meters per second in the opposite direction. Calculate the momentum at this instant, okay? So again, same mass. Let's write down this here, 11.34 is clearly going to be important. It's the same mass, that's 0.42, but this time it leaves at 20. So 20 times 0.42 is equal to 8.4. Okay, so we've got, that's going to be minus because it's going off in the other direction. Okay, so you definitely need to put a minus in there because it's got opposite direction. That's what the second mark is for. The first mark is just for the magnitude, second mark is for the direction. So technically, if I was writing this out again, I'd put a minus in front of my 20 there, although it's a given from the situation. So the ball remains in contact with the post for 0.22 seconds. So we've got the time for this change of momentum. Determine the average force exerted on the ball due to the collision. Well, we know that force is equal to change in momentum over time. Bless me. Right, so the force is equal to change in momentum over time. So a change in momentum is 11.34 take away minus 8.4. You've got to get that minus 8.4 in there. That's a common mistake. People forget to put that minus in there. Then you need to divide that by the time, which is 0.22. Okay, so it gives us about 90 newtons, so 89.7 newtons, which is approximately equal to 90 newtons. So there's 90 newton force in terms of this collision. Right. Next, show the direction of this force on the diagram. Okay, well, it's going to be going towards the left. Okay, so it's going from the right to the left. Okay, so if the ball of direction of motion originally was this way, the force must be in this way because it's pushing it off the post. The force is applied from the post onto the ball. Okay, state one difference and one similarity between this force and the force that acts on the post during the impact of the ball. So automatically, similarities and differences, you're thinking about Newton's third law of pair. So, just as a reminder, remember the similarities are the type of force, the duration of the force, same line of action, same magnitude, okay, and the differences are that it's going to have act on a different body, and it will act in the opposite direction, okay. So opposite direction acts on different bodies is fine, that's in the mark scheme. Same type of force, same size, acts on the same line of action. And they also have same size impulse as well. Okay, so that's question 1 complete. Question 2. So we've got a proton. Let's just talk about an elastic collision is one where kinetic energy is conserved. Note they say kinetic energy, not just energy, it's kinetic energy. So whenever talking about elastic collisions, you must use the word kinetic energy. Inelastic, kinetic energy is not conserved. So you've got a proton, you've got the mass of a proton, you've got the speed of a proton. Apologies if your 6 has come up not superscript. Has a head-on collision, with a stationary helium nucleus. A stationary helium nucleus, the helium nucleus is not moving at all. After the collision, the helium nucleus, which has a mass of 6.65 times 10 to the minus 27, moves off with a speed of 9.65 times 10 to the 5 meters per second. Show that the kinetic energy of the helium nucleus is 3 times 10 to the 15. So kinetic energy is half mv squared, and thereafter the kinetic energy of the helium nucleus. Okay, so half times m. Okay, minus 27 times. Let's bracket this to make doubly sure. 5 squared. Okay, so just the value straight away from the information we've been given. Okay, so that's about 3 times 10 to the minus 15, 3.1 times 10 to the minus 15. Brilliant. Okay, so straightforward half mv squared calculation. Right, next. How much kinetic energy is lost by the proton? Okay, how much kinetic energy is lost by the proton? So, essentially, it's the amount of kinetic energy the helium nucleus has gained. The helium nucleus had no kinetic energy beforehand, so all of this energy the helium nucleus now has must have been given to it by the proton. Okay? So the amount of kinetic energy lost is 3 times 10 to the minus 15. Okay, so if you want to see what's actually happened here, the protons, so here's stationary helium nucleus, in comes a proton, smashes into it, this now goes off, this goes off as well, but where did this get its energy from to allow it to go off? Well, it came from the proton, so the amount of energy this has lost is the same that this has now. Okay, so that's also 3 times 10 to the 15 in this one over here. Hence determine the speed of the proton after the collision. Okay, so we're using 3 times 10 to the minus 15, and we need to rearrange for V. So half mv squared is equal to ek. So V is therefore equal to 2 times the root, 2 times kinetic energy over m, all square rooted. Okay, so let's whack our numbers in that. So remember, the kinetic energy is the amount that has been gained by the helium nucleus. So I'm just going to carry my number forward, so I'm going to put answer in there. Actually, 2 times answer, close bracket, divided by the mass. So now we're talking about the proton, so we need the mass of the proton. 1.67 minus 27. Okay, and then we square root that. So it's 1, 2, 3, 4, 5, 6. Okay, about 1.9 times 10 to the 6. I think I've missed something there. Oh right, yeah. What we've missed out is the initial kinetic energy of this. We've forgotten to take that into account. Okay, so we forgot to figure out how much the loss actually is. So we didn't figure out how much kinetic energy it originally had. We figured out how much had gone to the helium, but we didn't figure out how much it originally had. I've just gone straight into the calculation. Sorry, I missed one step out. Okay, so the amount the helium nucleus has, let's get this clear across to you guys again. So it's 3 times 10 to the 15 has gone off with that helium nucleus. That's how much joules have gone off with the helium nucleus. How much came in? Well, we don't know. Whatever is left over here, that goes off over here with the proton. Okay, that's how much the proton had. So how much did this have as it came in here? Well, we can figure that out. That's just half mv squared with that mass and that speed. Sorry, I made a massive boo-boo there. Okay, let's whack this through properly now. Okay, so this is the original kinetic energy I'm figuring out. So the mass of the proton times y, the speed of the proton squared, halved. Okay, 27 times by 2.4. Put that in the way there. Times into 6 squared. Okay, so essentially take away 3 minus 15. Okay, so 1.8. There we go. So 1.8 times 10 to the minus 15. So that's the value we should be putting into the half mv squared. V is equal to the root of 2ek over m. So that's our kinetic energy. So 2 times that answer, the kinetic energy that's actually ended up going off with this proton. So that's 1.81 times 10 to the minus 15 joules. Okay, divided by its, let's put a bracket in properly here. Let's do that again. 2 times answer, close bracket, divided by the mass of this proton, which is remaining unchanged. 27. Okay, and I want the square root of that. Okay, so 1, 2, 3, 4, 5, 6, about 1.5 times 10 to the 6. Okay, so if you look at the mark scheme, that should be about the right answer. So, tricky question, can fall into a trap there quite easily, as I did, 3 marks. Name a quantity other than kinetic energy that is conserved in this collision. We're assuming momentum as well. Charge will also be conserved. Any of those ideas, generally other ones, so momentum, mass, charge, or the total energy of the situation, they're all conserved. Okay, question number 3. So feel free to just skip back to the mark scheme and double check those. I'm 100% sure I'm now right though. Calculate the total momentum of the 2 moving balls before the collision. Okay, so we've got Two balls coming in, they collide with some more balls over here. We need to calculate the momentum before the collision. Okay, so that's 2 times by the mass of the balls times by the velocity. So it's 2 times the mass times the velocity. Pretty straightforward. So if you put that through, you end up with 0.042 kilogram meters per second. Show that the kinetic energy of the two moving balls before the collision is about 0.019. Okay, so again, it's the idea of half mv squared. So a half times by 2 times that mass times by that velocity squared, and you'll get something in the region of 0.0185. Okay, so that's just the half mv squared calculation there. That is the P equals mv calculation there. If this is, by the way, if this is the first video you're watching after watching my AS videos, you'll see that I'm starting to skip through a few calculations, not write them out. The standard at AS is, sorry, A2 is higher, so only the trickier calculations will I actually sort of go through and write everything out. And I won't read through the entire question with you guys as well, although remember that's something that you should definitely be doing. State the condition required for the total momentum of the balls to be conserved. So remember, total momentum is conserved, it means there's no external forces. So in other words, the momentum isn't transferred to anywhere else. No momentum, so no external forces is the idea, no external forces. Show that the value in C8 has been calculated correctly. So C8 is speed after the collision. C8, okay, check that that has been calculated correctly. Okay. So we've got to figure out how they figured the momentum after collision, the velocity after the collision. So they must have used a momentum and divided that by mass. Okay, that's the idea. Velocity, remember, is momentum divided by mass. Okay, so our mass, remember, is our momentum, remember, is 0.042, and our mass is 0.072. We've got that over here. So remember, so the momentum from before, remember, of 3 moving balls is 0.042. Is that correct? Yes, it is. Yeah. So if you divide those two numbers, yeah, 0.042 divided by 0.072, and that gives you about 0.583, which rounds up to somewhere around over here. So that's fine. Okay. What would be a suitable formula for the calculation of D9? So D9 is kinetic energy after collision, so that's half mv squared. Okay, so half times by 0.096 times by 0.44 squared. Okay, so 0.5 times by D, so D9 is equal to 0.5 times by B9 times by C9 squared. Explain how the spreadsheet calculations show that 2 balls moving away is the only likely outcome of the collision. Okay, so how many marks are after this question? So 3 markers. So after a bit of a description in terms of what's going on. Okay, after quite a detailed description of what's going on. So let's actually have a look at this data. So if we look at the amount of kinetic energy that's actually released, you need a lot of kinetic energy for one ball. Okay, you need a lot of kinetic energy for one ball. So it can't be one ball because that's too much kinetic energy. Collisions are pretty much elastic, so there's not much loss of energy. So it won't be 3, 4, or 5 balls. So 2 balls gives the same amount of energy as what comes in essentially. So it can't be any of these because it's pretty much an elastic collision. Okay, it can't be that because there's too much in the kinetic energy that's actually put in. Okay, so it's got to be 2 balls. Got to be 2 balls. Too much kinetic energy, too much loss of kinetic energy. So therefore 2 balls. Pretty much elastic collision, so it's pretty close to the kinetic energy we calculated before. D. The 2 balls that moved away then swing back and collide. The pattern is repeated after a number of collisions. Depending on the quality of the cradle, the pattern breaks down. Eventually more than 2 balls will be in motion and they will not all have the same speed. So just while this occurs makes reference to the spreadsheet. Okay? So over time, remember, this is not a perfect situation. Kinetic energy will be lost. So as this kinetic energy is lost through sort of sound or deformation or heat or any of those sort of ideas, momentum will still be conserved. Okay, so remember, it's just becoming an inelastic collision. It is still a collision, so momentum is still conserved. So as the total kinetic energy is decreasing, more balls will be put into motion. So the momentum is still the same, but kinetic energy is going down. So you can tell from the spreadsheet that if kinetic energy is going down, there's more balls. Okay, so less kinetic energy, more balls released. Okay, so that's the idea. Okay, so kinetic energy will decrease with time because the fact is losing energy, so more balls will be released. And if I remember correctly, that is the end of ISP task 1. Okay, so thank you very much for listening, guys. And next time we'll be doing ISP task 2, which is focusing on the idea of circular motion. Thank you very much, guys.